Welcome to the Padhai Kar Lo JEE preparation channel. You can practice more problems on this exact topic on our Padhai Kar Lo Android app, link in the description below, or on our website padhaikarlo.com. Today's chapter is Trigonometry, a chapter that's less about learning brand new concepts and much more about building genuine fluency with a large toolkit of identities. Since JEE trigonometry problems are fundamentally about recognizing exactly which identity transforms a given expression into something you can actually solve. In this video we'll cover the core identities, compound and multiple angle formulas, trigonometric equations, properties of triangles, and inverse trigonometric functions. Let's begin. Every trigonometric identity in this entire chapter ultimately traces back to just one single foundational relationship: sine squared theta plus cosine squared theta equals 1, which comes directly from the Pythagorean theorem applied to a point on the unit circle, and dividing this identity through by cosine squared theta gives tan squared theta plus 1 equals secant squared theta, while dividing through by sine squared theta instead gives 1 plus cot squared theta equals cosec squared theta. These three Pythagorean identities together appear constantly, repeatedly throughout this entire chapter. The unit circle itself is genuinely the single best mental model for understanding trigonometric functions properly. Sine of theta equals the y-coordinate of the corresponding point, cosine of theta equal the x-coordinate. And this immediately, directly explains the ASTC rule. All trigonometric ratios are positive in the first quadrant, only sine and its reciprocal cosecant are positive in the second, only tangent and its reciprocal cotangent are positive in the third, and only cosine and its reciprocal secant are positive in the fourth. Trigonometric functions are also genuinely periodic. Sine and cosine both repeat with period 2 pi, while tangent and cotangent repeat with the shorter period pi, and knowing these specific periods precisely is absolutely essential for correctly finding the complete full general solution to any trigonometric equation, not merely one single isolated particular solution. Compound angle formulas express trigonometric functions of a sum or difference or two angles in terms of the individual trigonometric functions of each separate angle. Sine of A plus letter B equals sine A cosine B plus cosine A sine B, and cosine of A plus letter B equals cosine A cosine B minus sine A sine B, with the corresponding minus versions simply flipping the connecting sign in the middle, and tangent of A plus letter B equals tan A plus tan B, all divided by 1 minus tan A tan B. These specific formulas are genuinely, absolutely foundational, since a very large fraction of this entire chapter's remaining more advanced formulas are actually derived directly from just these two or three compound angle results. Double angle formulas follow directly by simply substituting B equals A into the corresponding compound angle formulas. Sine or 2A equals 2 sine A cosine A, and cosine or 2A has three genuinely equivalent interchangeable useful forms: cosine squared A minus sine squared A, or 2 cosine squared A minus 1, or 1 minus 2 sine squared A. And knowing precisely when to strategically use each specific alternate form, based on which particular variable, sine or cosine, you are actually trying to eliminate from a given expression, is a genuinely valuable, frequently useful practical skill. Triple angle formulas: sine of 3A equals 3 sine A minus 4 sine cubed A, and cosine of 3A equals 4 cosine cubed A minus 3 cosine A appear somewhat less frequently overall, but are still absolutely worth having directly, immediately available and ready for specific equation solving problems that explicitly require them. Sum to product formulas convert a sum or difference or two trigonometric functions into a genuinely more useful product form. Sine C plus sine D equals 2 sine not C plus D over 2 times cosine C minus D over 2, and cosine C plus cosine D equals 2 cosine or C plus D over 2 times cosine or C minus D over 2, with corresponding closely related but distinct versions for the specific difference cases as well. These particular conversions are extremely valuable and frequently needed specifically when you are trying to solve a trigonometric equation, or actually prove some given trigonometric identity that has terms simply added together, since a converted product form can then often be set directly equal to 0 and cleanly, easily factored, something a raw unconverted sum genuinely cannot be. Product to sum formulas work specifically in the reverse direction. 2 sine a cosine b equals sine of a plus b, plus sine of a minus b. And these particular formulas are especially useful specifically for integration problems in calculus, converting an otherwise difficult to integrate product of trigonometric functions into a much more easily directly integrable sum instead. A genuinely practical, useful memory strategy here, rather than attempting to memorize every single one of these formulas as entirely separate, disconnected facts. Recognize that they're all directly, systematically derivable from the compound angle formulas covered just previously, by strategically adding or subtracting the sine or cosine compound angle pairs together in different specific combinations. Understanding this underlying derivation genuinely helps you reconstruct any specific formula quickly and reliably, even in the rare event you genuinely momentarily forget its exact final form under real exam pressure. Solving a trigonometric equation means finding every single angle that genuinely satisfies it, and since trigonometric functions are periodic, there are always infinitely many valid solutions, so JEE specifically requires the complete general solution expressed cleanly using an integer parameter, conventionally n, rather than merely a single isolated particular solution. For sine theta equals sine alpha, the complete general solution is theta equals n pi plus ne1 to the power n times alpha. This specific, slightly unusual looking alternating sign form correctly, systematically captures every single valid solution across all four quadrants simultaneously. For cosine theta equals cosine alpha, the general solution is theta equals 2n pi plus or minus alpha. And for tangent theta equals tangent alpha, it's simply theta equals n pi plus alpha. This particular tangent case is notably the simplest of the three, precisely because tangent's own fundamental period is only pi, rather than the longer 2 period that both sine and cosine share. When actually solving a more complex trigonometric equation, the essential general strategy is to first reduce it algebraically down to one single trigonometric function, often by strategically applying identities covered earlier, and then to solve that specific resulting simplified equation using the appropriate one or these three standard general solution forms. A frequently tested, genuinely important trap. Always carefully, deliberately check whether any algebraic step you've taken, particularly squaring both sides on equation, might have accidentally introduced spurious, invalid extra solutions that don't actually satisfy the original equation, and verify final answers directly against that original equation before finalizing them. The sine rule relates a triangle's three sides to the sines of their three respective opposite angles over sine A equals B over sine B equals C over sine C, and this common ratio actually equals to r, where r is specifically the radius of the triangle's circumscribed circle, a genuinely useful additional fact frequently tested directly and combined with other triangle properties. The sine rule is specifically most useful whenever you're given two angles and one side, or two sides and a non-included angle, a triangle, and asked to find some other currently unknown triangle element. The cosine rule states that a squared equals b squared plus c squared minus 2bc cosine a, effectively a direct generalization of the ordinary Pythagorean theorem to genuinely handle non-right triangles as well, and it's most useful specifically whenever you're given all three sides, or exactly two sides, plus their one specific included angle cell. A triangle's area can be calculated in several genuinely useful different, equivalent ways depending on exactly what specific information is actually given. 1/2 times b times c times sine a, when two sides and their included angle are known, or directly via Heron's formula, the square root of s times s minus a times s minus b times s minus c, where s is the triangle's semiperimeter, when instead all three side lengths alone are known. Napier's analogy and specific projection formulas provide further additional relationships between a triangle's sides and angles and are occasionally specifically needed for certain more advanced JEE triangle problems. Since ordinary trigonometric functions are periodic, they're genuinely not one-to-one across their entire natural domain, so defining their inverse functions properly requires deliberately restricting the domain specifically to what's called the principal value branch, ensuring the function actually becomes properly genuinely invertible on that restricted piece. Sine inverse has domain restricted to the closed interval -1 to 1 with range restricted to -π/2 to π/2. Cosine inverse has that identical domain -1 to 1 but range restricted instead to 0 to π, and tangent inverse has domain covering all real numbers with range restricted to the open interval -π/2 to π/2. Getting these specific principal value ranges precisely correct is absolutely critical, since a remarkably large fraction of inverse trigonometric function problems on JEE are actually fundamentally entirely about correctly handling these specific domain and range restrictions, rather than about any particularly complicated underlying calculation. A key fucktly used identity, sine inverse x plus cosine inverse x equals π/2 for any x within the shared valid domain directly reflects the complementary relationship between sine and cosine. And similarly tangent inverse x plus cotangent inverse x also equals π/2. Composite function problems, evaluating something like sine of cosine inverse x, are extremely common and are most reliably safely solved by very carefully constructing a genuine right trial consistent with the given inner inverse function, reading the required specific ratio directly and safe of that triangle, rather than attempting to blindly apply a memorized formula that might not actually correctly apply to the specific given range in that particular problem. Beyond the basic complementary identity, several other inverse trigonometric identities appear frequently and repeatedly. Tan inverse x plus tan inverse a equals tan inverse or x plus y/1 minus x, y. But genuinely critically, this specific identity only holds true directly, without any needed adjustment, when the product xy is actually less than 1. If xy is instead greater than 1, you must add or subtract pi to correctly account for the resulting otherwise hidden branch shift, depending specifically on the individual signs of x and y. This exact condition is commonly the single most frequently tested trap throughout this entire inverse trigonometry topic. Similarly, the formula 2 tan inverse x equals sin inverse or 2x/1 plus x squared only holds directly and correctly for x between -1 and 1 inclusive. Outside that specific restricted range, the correct relationship instead genuinely involves pi minus that same expression. These aren't simply arbitrary, obscure restrictions to memorize mechanically, they arise directly, necessarily from the actual underlying principal value range constraints established earlier. So genuinely, deeply understanding exactly why these restrictions exist, rather than simply memorizing them as isolated, disconnected facts, is what lets you correctly, reliably handle unfamiliar variations of these problems that you genuinely haven't specifically seen before. When actually solving any inverse trigonometric equation, always explicitly verify that your final computed answer genuinely actually lies within the required principal value range. An algebraically correct value that unfortunately falls outside the valid, correct principal range must still be firmly rejected as invalid. For any JEE trigonometry problem, first genuinely identify exactly what type of problem it actually is: an identity to prove, an equation to solve, or a triangle property to apply, since each of these three problem types genuinely calls for a distinctly different, specific strategy and approach. For proving identities, work systematically from the more genuinely complicated side of the equation toward the simpler side, actively looking to substitute in Pythagorean identities or compound angle formulas wherever they clearly, obviously apply. For solving equations, first reduce the given equation algebraically down to contain just one single trigonometric function and one single specific angle. Then apply the correct appropriate general solution form. And always remember to explicitly state your complete final answer using the required integer parameter n. For triangle problems, immediately identify exactly what specific information you're actually given. Sides only keys directly for the cosine rule, or Heron's formula. Angles combined with sides calls for the sine rule. And correctly choose your working formula accordingly from the very start. Finally, keep a small memorized core set of standard angle values 0, 30, 45, 60 and 90 degrees genuinely instantly available without needing to think, since these exact values appear constantly repeatedly throughout this entire chapter, and any time spent needlessly rederiving them from scratch under real exam pressure is time that's been genuinely unnecessarily wasted. A frequently tested JEE skill is finding the maximum, or minimum possible value of an expression like a sine theta plus b cosine theta. Without needing to use calculus at all, this specific expression can always be rewritten in the equivalent single-term form, r sine or theta plus phi, where r equals the square root of a squared plus b squared, and phi is a specific phase angle satisfying tan phi equals b over a. Since sine of anything genuinely always lies between -1 and +1 inclusive, it follows immediately, directly that a sine theta plus b cosine theta itself always lies between -r and +r, giving you the maximum and minimum values instantly without needing any differentiation whatsoever. Maximum value equals plus the square root of a squared plus b squared, and minimum value equals the negative or that exact same quantity. This same core technique extends naturally and directly to slightly more complex expressions too. For instance, finding the range or sine squared theta plus b cosine squared theta, by first rewriting it using the double angle identity in terms of cosine or 2 theta, converting the original expression into that same single term r sine or r cosine form, recognizing quickly when a given problem is actually secretly just this exact single disguised technique rather than attempting a needlessly longer calculus-based approach involving derivatives, is a genuine, valuable time-saving skill specifically worth practicing deliberately and repeatedly before the actual exam. Let's recap this entire chapter. Every identity traces back to sine squared plus cosine squared equals 1, and the unit circle explains the ASTC rule and periods. Compound angle formulas generate double, triple, and sum to product formulas, all worth understanding as connected, derivable relationships rather than isolated facts. General solutions require the specific standard forms for sine, cosine, and tangent equations, and triangle properties use the sine rule, cosine rule, and area formulas depending on what's given. Inverse trigonometric functions require careful attention to principal-valued domain and ranges, with several key identities holding only under specific conditions, and always verify your final answer's range before accepting it. That's the complete trigonometry chapter for JEE. Keep the general solution forms and the inverse trigonometric principal value ranges sharp. They're the single most common source of lost marks in this entire chapter. If this video helped, please like it and subscribe to Padhai Karlo for more JEE preparation content just like this. See you in the next one.